Now, if we were having a real live class here, I would say, well, we've done alpha decay, we've done beta decay, what's the next one we'll do? And a bunch of the class would say gamma, because of course you've learned alpha, beta, gamma in previous material. Well, gamma radiation is not a type of particle. It's not a particle, it's electromagnetic rays of very, very, very high energy. So we're not actually going to think about that in our next decay consideration. Gamma radiation comes as a result of one of these other decays, alpha decay, beta decay, this mystery decay we're about to talk about, in which the result of the decay initially is an excited state of the nucleus that has much higher energy than it would like to have in the so-called ground state. So in the same way that an excited electron for an emission spectrum relaxes down to the ground state, emitting a photon of particular energy, so an excited nucleus will relax down to the ground state, emitting a photon of electromagnetic energy. It just happens that the energy levels for nuclei are much higher than the energy levels for electrons, and so the energy of that photon, that gamma photon, is extremely high. But we're not going to talk anymore about gamma radiation right now. What we are going to do is we're going to talk about positron decay. So this is our third type of decay in which a radioactive nucleus 1 kicks out a particle to turn into a new nucleus that may or may not be radioactive. What is a positron, you ask yourself? Well, it's a particle that has a charge of +1 and a mass of 0. What does that look like to you? Well, it kind of looks like taking a beta particle, but instead of that beta particle being negative, it's positive. Okay, now of course we would ordinarily say, well, hang on, mass of 0, charge of -1, that's an electron. So a positron can be thought of as being a positive electron. There's the words, contract them together, lose the tiv and the ilic, and you've got positron. Let's generate a fast nuclear equation for it. Boron 8 undergoes positron decay. What's the product? So boron 8 has got a mass of 8, charge of 5. Our positron has got a mass of 0 and a charge of 1. So look at our mystery particle, mystery nucleus, product nucleus. It's going to have a mass of 8 and a charge of 4 to get everything balanced out. What has an atomic number of 4? Beryllium. It's got a mass of 8, so therefore that is beryllium. 8 is our product. Again, if we think of it in terms of our protons and our neutrons, boron 8 has got 5 protons and 3 neutrons. Beryllium 8 has got 4 protons, 4 neutrons. So what we've effectively done is we have lost a proton, we've gained a neutron. We have turned a proton into a neutron. There you go, that's the proton, neutron. The difference between them is a positron kicking out there. Just making sure the masses and the charges balance out. Proton on the left, mass and charge of 1. Neutron, mass of 1, so that's the mass taken care of, has a charge of 0, so we've still got a charge hanging, and so therefore the positron, mass of 0, charge of +1. Now, some people have been known to say that the positron decay is the opposite of beta decay. No, it's not, right? A positron is the opposite of an electron, but in both cases, the decay kicks out a particle. The actual opposite of beta decay is so-called electron capture. This is one in which that unstable nucleus just reaches out into its 1s orbital, or the low-lying electron orbitals, grabs itself an electron and turns into a second nucleus. Unstable nucleus doesn't need any help, just grabs itself one of its own electrons, turns into nucleus 2. So you can see this is the opposite of beta decay. Nucleus 2 kicks out a beta particle, an electron, leaving nucleus 1. Again, we'll do it excuse me, for boron 8, because pretty much positron decay and electron capture give us the same things. They happen to the same particular nucleus. So if we take boron 8, give it an electron, what's the new nucleus that is formed? Well, we know this, don't we? Mass of 8, charge of 5 for the boron, mass of 0, charge of -1 for the electron. So on the left hand side we've got a mass of 8, thus the right hand side needs a mass of 8, left hand side charge of 4, so right hand side needs a charge of 4. Thus again, electron capture turns boron 8 into beryllium 8. Again, think of it in terms of our proton and neutrons. We've got a proton, we give it an electron, it turns into a neutron, because the total mass of 1 for the proton, 1 for the neutron, 0 for the electron, 1 charge for the proton, minus 1 charge from the electron, put them together, charge of 0 for the neutron. So there we are. We've discussed alpha decay, beta decay, and positron decay. We've also mentioned gamma radiation. Now, the next movie, we're just going to talk about the properties of these, the alpha, the beta, and the gamma, in terms of how they behave in a magnetic field and their role as penetrating radiation. We'll also talk about the kinetics of radioactive decay, its first order. And so everything we did associated with first order reactions back in the kinetics module, we can now talk about in terms of nuclear decay. And then finally, in the core material, I'm going to discuss something that's not on at least the WJEC specs, and that is what factors make particular nuclei decay or not. So in other words, what factors make a nucleus stable or unstable, and if it's an unstable nucleus, why do some go alpha, some go beta, and some go positron/electron capture?